somewhat contains a stochastic part of the data. Because the data are changing because, you know, it's changing the setting, the content, the measurement that you do about the data. You acquire the data, then you acquire the data again, you know, it might change because of the noise, because of any stochastic part, because of some unpredictable part, okay? Because otherwise, you know, if I can predict and, you know, model everything, then there will be no class, right? Because, you know, everything is predictable. And then we can make as much money as we want about, you know, investing money in stocks, right? So that unpredictable part is not because it's unpredictable. It's because you cannot model it. And so I go back to the point. You remember, noise is that component that you cannot model for your system. So the interference, for instance, is not interference. It's a speech of someone else. But for me, I don't care what the other says. And so that is interference, that is stochastic part. So I prefer to model in that the other way. So anyway, so going to the point, you know, what we saw last time, we saw that because of the fact that x is the measurement, okay, and theta hat is the estimate, okay, is a function. Consider as a function. The technical word of this function is called statistics. Right? So the statistics is any transformation about the random vector xn. Xn is the dimension n of the vector. Okay? Then, you know, since I repeat many times, what I got this. This one is the distribution. Look at the word. Look at the meaning here, because every label has a meaning. So I mean, learn that every label is put in the place because of meaning. This is the probability density function, distribution, theta hat. So the estimated theta, okay, given that the theta is equal to theta 0, which means assuming that this experiment is that one. Huh? Now, this means that if the true theta is there, the distribution of the estimator might be this. If the true theta is not there, is there, the distribution might be different or the same. Okay? So if it is the same, then, you know, the distribution of the estimate is shifting with the value, but it might be different. There is no reason for being the same. So our goal is to establish how close we are to this true value. Now, let's just set the point about that. When you make, so our goal is to design the estimator, this one. Our goal is to get this one, but we're not happy just having the estimator. We need to give the performance of the estimator. So when we say my estimator is this, you need to say my estimator is this, and my accuracy is this one, and my uncertainty is the other, and you can set, I don't know, within my estimate value is within this interval with an accuracy of, I don't know, with a probability of 95%. Now, this is the numbers that we are developing. So when we say we design the estimator and with the performance. Having the estimator, I would say, is in some cases not complicated. Remember what we did with the stocks, okay, making the predictive model by the Apple stocks. What we did, you know, we predicted the value of Apple stocks, right? And, you know, we set an estimator. That was linear. We solved by the least square model, the least square solution. So now we can do everything. So we can go outside and say, okay, the class is finished for the end of the semester. So what is next? Next is that, you know, we want to know what is the accuracy of that estimator. I want to know how accurate I can get the stocks value in the predictive model on Apple stocks, or I don't know, Amazon stocks, or I don't know, Qualcomm stocks, Intel stocks, and so on. Okay? Sorry, I know only the stocks in my field, so you know, this is the stocks. Okay? So I know there are Tesla stocks, right? It's going down because, you know, the chief, you know, made some declaration that he shouldn't have done. Anyway, so this is what I know. So anyway, so this is our goal. Okay, this is our goal. Now we need to define two properties. First of of all, when I take this distribution, you know, this distribution has a mean. And the mean of the distribution is the body center, okay? Now, by the way, I also, you know, described this bell shape, which is a Gaussian. So what I can say is that this distribution is not Gaussian. This one is not Gaussian. Okay, so it might happen that my distribution is not at all Gaussian. So this one is one possible distribution, but you know, that one is not Gaussian at all. So now the mean here is the body center. Okay, so don't make it confused about the body center. Body center means that, you know, the area of this part is the same of the area of the other side, the other part. Okay, so that's the meaning of the mean of the random variable. Okay, the mean is just the same that, and which is the same meaning of, you know, the body center in any physical structure. Okay, and then we have another parameter, the distribution. So the dispersion around the mean, and this dispersion is measured in terms of this dispersion is measured in terms of deviation from the mean. So that one is, you know, is in some cases called the variance of the estimated quantity. Again, you know, the variance is nothing else than the same quantity which is measured in mechanics, which is called inertia. So, you know, every engineer is measuring the same stuff. So they are measuring inertia, we measure the dispersion. We measure the mean, they measure the body center. I mean, at the end of the story, we are all engineers are doing the same job. Now, let me move forward. So the accuracy, by the way, so ideally, what I would do is that, you know, ideally I would have my distribution around the truth. It's impossible, okay? So what I want to do is that this error is as small as possible. Now give a metric about this dispersion. Now the metric are the following, you know, one of the metrics is called bias. So the bias is the distance between the mean and the truth. This one. That distance, the mean of the dispersion and the true one. Okay? So this is called bias. So, you know, beyond of the word, the bias is this B. So in formula is the expectation with respect to x. Why? Because x is the only random term. Okay? So is the expectation with respect to x of what? Of the error. And the error is the error between the true, okay, and the estimated value. So this is, you know, the meaning of the error. So the error, you know, is theta hat x with n samples minus theta 0. Okay, but since the expectation is acting only on theta hat, because it depends on x, and not on the other, so this comes with the second part of the formula. Okay, so this is the bias. Now we can say that an estimator is unbiased if this one is 0. Or we can say that an estimator is asymptotically unbiased when this property is guaranteed for n is going to infinity. Now, this is the mathematical way to say. Now, what is the engineering way to say? We never have infinite samples. Okay? So we never. So forget about it. So engineering, we say that, you know, this is asymptotically unbiased when n is large enough. What does it mean large enough? Yeah, you know, it should be large. So if I take a large enough number of samples, then, you know, that one is going to 0. Now let me explain about what does it mean large enough, because, you know, we will use many times. Let's consider with this a stupid example. Okay? So what is the bias? Now the bias, you know, is the expectation, okay, as is written there, okay. So it's an expectation with respect to x of theta hat, depending on x, minus theta 0, okay. Let's take a scalar. So that one is a scalar. This is the bias. Now you know this one depends on n. So we know that asymptotically 0, but you know, we cannot use the asymptotic properties. because we never have infinite samples. So that means that in engineering setting, okay, we can tolerate some bias. So that means that, in engineering we say that I can say that this number should be smaller than a small bias, epsilon bias. This is small, very small. Okay? Because about the engineering setting, because the context of engineering we are working. So for this reason, I don't do anything with the property that is asymptotically unbiased. What I need to get is, since I put this as a, this is a technical specification, which is called specs. Specs means, is required by the project. So the project requires that, the frequency should be accurate within 1%. That is a specs. The position should be accurate within 5 centimeters. That's the specs, you see? So according to that specs, by manipulating, I get this number. Then, from this, I get that n, this is smaller or equal than that. If n is larger or equal than, 350. So for engineering point of view, 350 is the asymptotic value which makes the bias to be tolerable by the system. And then, is when I say, the number of samples should be large enough. This is large enough. If n is larger than 350, so it's larger than a certain value, for me the bias is equivalent to be 0. Is it clear? Okay. It's a subtle concept. Huh? So mathematically, fine. But we are engineers, so when we work with the tolerance. And the tolerance is constraint us to have, the tolerance of, 1%, 10 to the minus 4, 10 to the minus 5, depends on the case. Okay? So this is just to explain large enough. Okay? As indicated here. Large enough. Now, what is the, assume in this case, theta 0, is fixed. Now, if theta 0 is varying, then what I need to compute the so-called Bayesian bias. The Bayesian bias, you look at the formula of the previous one, and here. Now the Bayesian bias, is different from the previous one, except that now the expectation is computed with respect to theta 0. Because theta 0 is itself, a random variable. Then, because of that, I can calculate, my Bayesian bias, which is by computing the expectation with theta and x of this estimated value, minus the mean value of the parameter theta. Okay? So of course this one, depends on the distribution of theta, which should be known. Okay? So this is the accuracy of my estimator. Now, we will learn how to establish, we will learn how to calculate these accuracies, and then we will learn to set these values, and we release our estimators, which means, we give our estimator, to the customer, to someone that committed you. Because, someone comes to your office and say, I need to solve this problem. Okay, but it's not over. I need to solve it with this problem, with some accuracy, with some uncertainty, with some of this, with some of that, because when you give the answer, okay, so the second question they ask you is, what is the accuracy? What is the confidence? And then you need to have the answer ready. If you have no answer on that, they go to someone else. Okay? So, now, a next metric, remember, this is metric number 1. Okay?
In this case, we are assuming that theta and x are statistically independent, right?
No, theta and x are statistically dependent.
Dependent.
Yeah. It should be. Now, okay, what I need to compute is the mean square error. Now, a mean square error is another common metric. Now, the mean square error, is very simple. It's the second moment of the error. Now, in a deterministic setting, non-Bayesian setting, okay, non-Bayesian mean square error, which means non-Bayesian means theta 0 is deterministic. Okay, this is the meaning. So my parameter is non-deterministic. The frequency of the sinusoid, the position of the target in a radar system. Okay, I don't know. It's think about whatever you want. Okay, the propagation speed in the table, that is deterministic. I don't know what is the propagation speed, but the propagation of the elastic wave in the table is deterministic. Okay. So anyway, so that is the meaning about deterministic. Now, what is the mean square error? Now, the mean square error, is the second moment. Okay, so that one is delta theta hat. That depends on x and okay. And this one is the second order moment for that. Okay, this is the mean square error. So it's how much the mean square deviates. Now, what I'm measuring by the mean square error, is an integrated measurement on the error. Now, let's consider, okay, to make it simple, to make it more understandable, let's consider the case where, the number of parameters is 1, p equal 1. So since p equal 1, the theta vector is equal to theta. Okay, it's a scalar. Since it is a scalar, I can handle my metric more easily. So what is the mean square error now? So the mean square error is theta hat. Now this one depends on x. So I skip some of the dependency. So that one is theta hat minus theta 0 to the square. Okay. So that one means that the expectation of theta theta 0, okay, can be replaced by summing and removing the expectation with respect to theta hat, okay, which is my summing and removing. Then when I blah blah blah, I make some analytical manipulation. Then I get that the mean square error is the variance plus the square of the bias. Interesting, this story. So that means that if I want to make the mean square error small, I need to have made the variance small and the bias 0. Because that is the best way to make the mean square error as a minimum. So if I want to minimize the mean square error, I need to have 0 bias and a minimum variance. Clear? Now remember this story. Okay, about as a rule of thumb, the mean square error is a sum of variance plus a bias squared. Now the reason why I stress this point is because when we do lab or exercise or numerical or some blah blah blah, you get some surprise because you say, I made everything to make a variance small. So for you, the result should be very good, but anomaly, strangely, it comes a strange result. So you have a mean square error which is big, and according to your analytics, it should be small, and you don't know where it is. So you come and say, I don't know, the minimum should be there. The theory says that I should have this performance. The mean square error should be there, but it's bigger. Okay. Now remember always, since the mean square error is the sum of variance and bias, if you, according to your theory, you try to make an estimator that has a variance quite small, but you forget about the bias, so that probably indicates that you have a bias. Okay. Tell me.
According to which knowledge you consider those two are orthogonal, so you conclude that the multiplication of those two terms is 0.
Where is the multiplication?
Okay, by doing the square,
Do it.
okay, then it's obvious that you consider the multiplication of these two terms is 0.
I didn't do that.
If you expand it,
Okay.
then the first term is variance, the second term is bias square, the
Yeah.
third term is multiplication of these two.
Yeah, but that one, is theta hat. Okay. That one is random. That one is deterministic.
Okay.
And then is 0.
Random times deterministic, then you.
Okay, so you take the expectation of the random. This is the random in theta.
Mhm.
And that one is deterministic. Then you take the expectation, try yourself. So, you are, the way you are doing, you are wasting me time. Okay. You have the expectation, what you say is that I take the square of the first, square of the second, then I have 2 times, right? Then I have theta minus expectation of theta, okay? And then the second one, right? Okay, it's expectation of theta hat minus theta 0, right? Is that what you say? Okay, now this is a number. You agree? Okay, now compute this expectation goes inside. So that one is expectation of theta minus theta. Okay? Now you understand why I say you are wasting time. Okay?
Sorry.
So, it's okay. So this is the formula you need to keep in mind. Okay, about that the mean square error is the sum of 2 terms. Never forget the bias. Never forget the bias. I said again, never forget the bias. Because you need to be sure that there is no bias. Always. Now, I can generalize, which is what I illustrate here. I don't derive, otherwise, we stay here for 3 hours. I don't derive, okay? But so the mean square error again, okay, it can be calculated as a matrix. So this matrix is the vector of the error multiplied by the Hermitian of the vector of the error. So, vector of the error time vector of the error, Hermitian. Okay, Hermitian because it's a complex conjugate of every entry. Okay, so that one, if you make all the steps, including this, okay, you got that this one is a covariance of the estimate plus B Hermitian. Now remember, this is the vector of the bias. And this vector of the bias, okay, comprehend, the bias for the corresponding terms and the cross bias. So take at a time, please, put a note somewhere, take at a time to understand yourself, because I can repeat it 1,000 times, it doesn't make any sense. So there are something, I don't know, I think you understood, because you are not the first year here at the university, so you understood that there are something that you need to get convinced by yourself. So you take this here, you see, you write every piece. Now I cannot understand the sensitivity of each one of you. If you need to write every piece, if you like to write it in a stencil form, if you like to write as a summation, whatever. But you can see, you can write it, and then you understand. You say, here it is. What is the meaning? Okay. So that is the mean square error matrix, okay, which is the most general. Now, this is what I illustrate in this way. So the entry ij of the mean square matrix, is the covariance between theta I and theta j, estimated, time plus the bias on I and the bias on j. Okay, so this is how it is. Along with the diagonal entries, which means along the diagonal, these are exactly the variance of theta and the bias to the square, which is exactly the mean square error for the specific variable. So this is the most general. Let me write, just to highlight. This is the generalization to p variable. Now, again, you know, let me highlight again. Remember that. Okay, remember that. Now, you forgot the bias. The reason why I'm stressing, repeating, blah blah, is because at a certain point you forgot the bias. So for you, minimize the mean square error means minimize the variance, which is not true, provided that the bias is zero. Now, about the Bayesian mean square error, okay, the Bayesian again, now theta is no more deterministic, it's random. Okay, now, since that one is random, then the mean square error is obtained by expecting x and theta. Now, this expectation x and theta means all the x, all the theta. Okay. Now, another way to compute that is by the conditioning formula, which is I calculate first the mean square error for a fixed theta, then I average all the theta zero. Now this one is very important because this is the mean square error for theta equal theta zero, which means deterministic. Okay, which means C star, and star is this one. So the two metrics coincide. So that means that in order to compute the mean square error there for bias is the mean square error for deterministic, and then I take the expectation over theta, which is now becoming there. Okay, I think we have already done. Now, one more. We are lucky in life because we have performance bound. Okay, what are performance bound? Performance bound says that we have the theory which is telling us that the mean square error, okay, it cannot be lower than a certain value. Excellent. So that one is really helpful. Now let me describe the point. Let's see. Let me describe the point. For instance, the mean square error is measuring the dispersion. Okay. So imagine that we have a certain experiment, xn. Okay, is a certain signal depending on n, and then on a set of parameters theta. There is some noise, Wn. Okay. Well, let's make just an experiment. Now, so this is the noise. Let's assume that the Wn, okay, is normal with zero mean and power sigma W. Okay. Let's say that, I don't know, for some reason, okay, this signal is multiplied by A. Okay? A sets the amplitude. Okay? So the bigger is A, the bigger is the signal. Okay? So let's expect that the bigger is A, the bigger is the power. So what I can do, my goal is to estimate theta. Okay? Let's make simple again. Theta is a scalar, so we have no trouble about the vector. So my goal is to estimate that theta. Now this model can be representative of a sinusoid. This model can be representative of a delay signal. This model can be representative of different combination of signals and so on. Now, so my goal is to estimate it. Now, imagine that I get my estimator. Okay, so what I do, I have my magic estimator, theta hat, which is using a set of samples, so x1 up to xn. Okay, that I prefer it to indicate as x vector n. Okay, so my estimator is taking this set of measurements. Now, I can make an experiment, so I can make a numerical experiment. I can use my MATLAB. I make a simulation. I simulate the system such as the system is generating that way. And I want to see how accurate is my estimator. So, you know, what I get is what I expect. I expect some easy stuff. If, you know, if A square, which is the square of the amplitude of that signal, I normalize with the square of the noise, okay? And let me call this parameter is similar to the signal to noise ratio, but you know, call just the parameter A squared divided by sigma squared. Now, if this one, you know, is getting large, okay, so as soon as this ratio is growing, becoming very large, okay, so it's going up, then what I expect that the mean square error on theta hat is going down because the error is small. That is what I expect. Intuitive. I don't do any computation, right? Okay. So, you know, mean square, I mean, as soon as that one, let me sketch it the other way so it's clear, okay? So when A squared divided by sigma squared W is going up, then mean square error is going down. And of course it's the opposite, right? Okay, very simple. Huh? Then you know what I can do. I can plot, now I can represent the plot. That, by the way, in MATLAB is just plot. Okay, so I can make a plot representation of the A squared divided by sigma squared W, and then I represent on the other axis the mean square error, okay, which is the mean square error on theta hat. Okay, now, so what I get, you know, I can take a different estimators. By the way, usually, typically, the axes are, these axes in log scale, and the other axis is in log scale. Sometimes it's called in decibel, but it's not necessary, okay? If you don't know what is decibel, you can survive, okay? So it's in log scale, that's important. Now, when you make this experiment, okay, this hypothetical experiment, I give the data to 10 people, and each of the 10 people, you know, can make a different experiment. And so what I get is, I don't know, I get the person number 1, which is set to this value, okay. Then I have a person number 2, it's going the same as person number 1. Person number 3, and then, you know, I have a person number 4. Okay, so what I notice on there? Well, I noticed that these are different possible estimators. So number 1, 2, 3, 4, right? Let me schedule. I don't know. I give them number 1, 2, 3, 4. Okay, these are different estimators. Okay? So, I mean, you would prefer what? You prefer number 4 from this point on. So when the signal to noise ratio or this ratio is larger than this value, you prefer number 4. When this ratio is smaller than this value, you prefer number 1, right? This is what you get. So what you can establish here is that, you know, here 1 is better, here 4 is better. Okay? Am I right? Doing nothing, okay? So, but you know, I mean, given in this way, I ask myself, can I do better? Because, you know, if I choose 4 people, I get 4 different estimators, different performance. So, can I choose, I don't know, can I search for another one? Can I search for a better? Can I see if number 4 is real or fake? Because, you know, you buy it. So you buy estimator, you put the money there. Okay? Now, then the bound, and we will study a Kramerl bound. So the bound in mean square error is saying that there cannot be any estimator which has a performance better than the bound. So imagine now that the bound is this one. This one is the mean square error bound. Okay? So that means that there cannot be any estimator that has a performance better than that. It's theoretically impossible. Okay? Now this is crucial because first of all, we know that number 4 is a fake. Okay? Because we are comparing with the theory, huh? And then number 4 is a fake. Then, okay, so this is what we get by the camera, this mean square bound. 4 is a fake. Second, we are better to choose 1. Okay. Third, we can say that 1, 2, and 3 asymptotically reach the bound. One, two, three. Now, if my operating region, so if I have an electronic system, I have a system, a measurement system, vibration system, prediction of the stocks system, whatever you like, okay. So, and if my system is operating in this region, then there is no reason to search for a better estimator because these 3 estimators are already reaching the bound. They're already optimal. So I can choose between 1, 2, and 3 depending on, for instance, the cost, number of operations, similar. Okay? So that one is crucial, and this is the crucial usage of the bound, of the mean square error bound. Okay? Now we will see that these mean square error bound we will derive by using the so-called Cramer-Rao bound. In short, CRB. Okay. So that we will say that there is no estimator that are going as good as the Cramer-Rao bound. So I can find an estimator that is reaching the Cramer-Rao bound asymptotically. I can find an estimator that is going as much as the Cramer-Rao bound. I cannot find any estimator that is going lower than the Cramer-Rao bound, unless it's a fake or using more information. Kind of saying 1, 2, 3 are using the data. Number 4 knows that the data are taken from there, and then since there, I don't know, it's the weather, and since or rainfall, and since these data are taken from the rainfall in I don't know in North Europe, and it's very rainy there, so I put that as an additional a priori information. Okay. Done.
For this solution, do we need unbiased assumption for all the estimation?
I didn't say it's unbiased. Okay. That is a mean square error. Good point. I'll come in a minute on that. Okay? So, that is just on a mean square error. Now it's out of any question. Now let's follow his reason. Okay, so he's asking, there is no mention about the bias. Where is the bias here? Now let's assume that I have an estimator. A very strange behavior. My estimator, is better. So this is number 5. That one is going good. Then at a certain point, is reaching the floor. So in principle, this should go down. What is this floor? Now usually when you have this kind of floors, this mean square of floor they are typically done by the bias effect. So the variance that is going down, but you know, I have a remaining very small bias in my estimator that I can notice on the mean square error flow. Now, sometimes, you know, this flow is due to some quantization effect, is due to some impossible to reduce noise or similar. We will see something like that. Okay? Now, let's move a little bit forward. So since now I made a better picture, okay, but that's the same story. So since now, you know, the mean square error is a variance plus a bias to the square. So what I can do is that, let's assume that I want to minimize the mean square error. And the very easy way to minimize is to say, okay, let's start to minimize the variance and put the bias to be 0. Okay? Because, you know, if I want to minimize, I have this plus that. They are both positive. So let's try. I can either minimize both, or, you know, if I have a possibility to put one of the terms 0, this goes to 0, and then I work on the other. Okay? Now, these kind of estimators are called minimum variance unbiased estimators. Unbiased is the word that characterizes, you know, the bias which is 0. So the minimum variance unbiased estimator are those estimators that have a 0 bias. Okay? So when I say minimum variance unbiased estimator, when I say unbiased, I'm implicitly saying that the bias is 0. So if I say that, it means that I need to optimize, you know, with respect to the variance. So what I need to do is, look, it's a minimum variance, MV. So minimum variance unbiased, okay? So it's minimum variance. I need to minimize the variance. So that is the rule that I'm going to apply. So minimize variance bisecting bias equals 0. Okay? This is the rule, this is the MDU. Now, you know, they're not very easy. Now, this one is telling you, is showing you the same, you know. Now, I set the bias to be 0, then I have 3 estimators, estimator number 1, estimator number 2, estimator number 3, and the lower bound, the Kramer-Rao bound. Okay, so if we are working with this, and you know, in this axis, not a signal-to-noise ratio now. In this axis is the specific value of theta. As you remember, I said that the distribution of error might change with theta. Okay, so this is the case. So imagine, you know, that I now draw the variance versus theta, assuming it's bias. So this plot is for bias equals 0. Okay? And so, you know, what I get, I can see that, I don't know, for instance, theta 1 and theta 2, they are, you know, within a certain region, one is better than the other. If I look at theta 3 is uniformly better. And, you know, and here touches the bound. Okay? So, when an estimator is touching the bound, I can say that the estimator is efficient. When it's efficient means I cannot use the data better because it's efficient itself. So an estimator is asymptotically efficient if, you know, it goes as much as the Kramer-Rao bound for some asymptotic value, or an estimator is locally efficient, like here, but, you know, I mean, outside of this region, the estimator is departing from the Kramer-Rao bound. Remember, the Kramer-Rao bound says I cannot do better than this. Now, since, you know, in general, the minimum variance unbiased estimator is not easy to get, let's start with the linear version. So let's derive the linear, so the minimum variance linear unbiased estimator, which is called the blue. Blue stands for best linear unbiased estimator. So let's derive that. What is blue? So blue, you know, is linear. Okay, So it's the best linear estimator. So let's assume, let the observation to be linear. Okay, so let's take the case where the observation are linear, just to make it simple. Now, if the observation are linear, doesn't mean it means that x is obtained by a matrix times the parameter theta plus w. Okay. Now this problem can be identification problem. We saw where I write, as we did a couple of days ago, I can write the filter by a matrix notation. I can write the input by a matrix notation. Okay, those are a couple of examples. So let's assume that I have my data, which is obtained by taking linear transformation of x plus w. And then I know that the noise, okay, is characterized by a mean that is mu w and the covariance cw. Okay. I'm not saying that the noise is Gaussian. I'm not only saying that the random variable noise has a mean that is, has a defined mu w, and the covariance is cw. Okay. Now, what is the linear estimator? Look at the word linear estimator. Linear estimator is a linear transformation of the data. That's a linear estimator. Now, this rule is general. So any linear estimator is an estimator which is a linear transformation of the data. No matter. So, no matter. So that means that theta hat is equal to any linear transformation. So it is A times x plus b. Simple. Simplify. If this one is p times 1. This one is p times n. And this term is p times 1. Let's make very easy. So let's consider that p is equal to 1. Now, if p is equal to 1, theta 1, okay, is equal to, it's a row, column is a row multiplied by a set of measurements. X1, x2, xn. And then I have A11, A12, A1n. Okay? Clear? So, since this one is x, since that one, I can call it A1, but that one is it's not column vector, it's a row. Then, I can represent it this way. So, in a scalar form, if you like the scalar, you're better to forget the scalar one, but if you like the scalar one, this one is 1 k equal 1 to n, and then it is xk. Okay, that's a linear. Okay, so this way of representing a linear estimator, I write it, forget it. Get the aptitude to write the estimator in this way, using matrices and vectors. Okay. Plus b, so there is b1. b1 is just a constant. So plus b1, which I represent as a1 transpose times xn, or just x, plus b1. This is my estimator for theta 1. So, if I consider p equal 1, if I consider many p, then what means? It means that there are many rows like that. So, let me now represent in a general sense. Page. So now, let me generalize the representation that we have here, okay? So what I have is that, I have theta 1 is equal to A1 transpose x plus B1. Theta 2 is equal to A2 transpose x plus B2. 2 theta p is equal to AP transpose X plus BP. Okay? That, you know, I can put all these into a vector. And this is the theta that I was describing. I can put all these A into vector. Is the vector? It's a matrix, right? Because that one is, you know, it's a matrix which is composed by A1 transpose, A2 transpose, AP transpose. Okay? That one is A, X remains there, and this is B. So this is the reason why, you know, I write that theta, which is the vector, is equal to A, the matrix, time X, the measurement, plus B. Okay, this is the linear estimator. So right now, you know, this is a linear estimator, it's not blue. It's not the best linear unbiased estimator. Now, let's analyze the words. The words say best. Now, the best means minimize. Okay, minimize the mean square, if you like. Linear. Okay, linear, we use it. It's just, you know, because it's just a combination, right? Okay, that's, you know, that's a rule. Unbiased. Well, if I need to say unbiased, let me write the unbiased. What does unbiased mean? So it means that, you know, I need to write the formula for the unbiased, which says the expectation of theta, this is theta hat. This might confuse me. Okay. This is theta hat. That's the name. So theta hat is equal to AX plus B. So the expectation of theta hat arbitrates, okay, that one depends on X. It's a function of X. Minus theta K, this should be 0. So unbiased means that, you know, it's set to 0. No question about it. Okay? Now, so how is it that it's 0? So let's see what does it mean theta hat K. So theta hat K means that I have the expectation, okay, with respect to X. So theta hat is simply AK transpose multiplied by X plus BK minus theta K. This should be 0. Okay? Let's make it. Again, you know, let's make it. So now you know what I can get. I need to see what is X. What is the property of X? So I need to go to the property of X. Now, let's make a one by one. Okay. So, now, what is the X? So let's consider that X, I said, is linear. So X is equal to H times theta plus W. Okay. So you know, let me calculate that. Let me add the page. Okay, now what I need to do, I need to plug this one inside here. And my expectation, which is with respect to the random X, now the randomness of X is due to the randomness of W. So now when I plug into there, I continue with the formula, plug in there, and I write here. So that one is expectation of, so it is AK transpose multiply. Now I plug it, H X H theta plus W plus BK minus theta K equal 0. Okay? Using the constraints of that. Move forward. Now, what is age? No, sorry, I was saying. Now, the expectation now is computed with respect to W, because W is the only random term. Okay? So, let's make it understand. So, what I can compute is the following. That here I have A K transpose multiplied by H times theta. Then I have a plus BK minus theta K. So I group the deterministic part plus AK transpose multiplied by H multiplied by W. And then I compute the expectation of that. This is equal to 0. Okay. So I move this here, okay. All that goes here, and all the other goes there. Okay, that's simply grouping. Now, I know that the mean term is mu. So what I do is, this one becomes AK transpose times mu W. Okay? So I get, I get the condition now. The condition is the following. In order to avoid the bias, what should I get is this. Now, what is H? H is composed by a set of columns. So I have H1, H2, and then I have Hn, okay, HP. Okay. So now that one means that AK is multiplying H1, AK is multiplying H2, AK is multiplying H3, and so on. Okay. Then, that one, everything is multiplying theta. Now, so I have AK transpose H1 is multiplying theta 1 plus B plus minus theta K. That one is a condition that should be equal to 0. So that one is setting a set of conditions to be fulfilled in order to guarantee that the bias is 0. And it's a set of conditions that is written on the relationship between H and A. So I have A K transpose H1. Okay, this is a scalar. Okay, multiplied by theta 1. Then it is plus AK transpose H2 multiplied by theta 2 plus blah blah blah. And then I have a AK transpose HK multiplied by theta K. Then I have plus BK minus theta K finally, and then plus the other equals 0. Now I have a set of conditions. In order to avoid the bias, unbiased, I should have AK transpose multiplied by HI should be, now what should be? To avoid the bias, these should be 0. These should be 0. This one should be 1. Because if that one is 1, I have theta k minus theta k, which is good. Okay? So my final condition that I get is ak h high is equal to 0 for any k different from I. And it is 1 for k equal 1. Which means that I can rewrite as delta k minus I, which is a Kronecker delta. The Kronecker delta says that it is 1 only when the two arguments are the same. Now, so good, I made 1, and then what's the other? Well, the other is that the bk should be equal to A transpose multiplied by mu w. Okay, so the other condition, so condition number 1, condition number 2 is that, bk should be equal to minus ak transpose mu w. Now, good. Now, let's see. What does it mean, that condition? That one, A transpose HI. Now, you can prove yourself that if I have a matrix like, I don't know, I have a matrix where, I have a set of entries. Here. And then I have a matrix A. Then I have a matrix H where I have all the columns. H1, H2. Okay? So if I have A1, H1 is 1. A1, H2 is 0. A1, H3 is 0. So what does it mean? That A multiplied by H should be identity. Right? That condition is the condition such that the matrix A generalized, the matrix A multiplied by the matrix A, H, should be equal to the identity. That's and in the extensive form, that's in the compact form. Okay? Unfortunately for you, it's not finished. Okay? So I only used, in this way, I get the condition on H, so on A, and then I have a solution for B. So assume that I know A, I know also B. So B actually is dependent on A. A is dependent on H, but B depends on A. So once I know A, matrix A, I know B as well. Now I take, this is not in the slides, okay, so I added so that you have the derivation. You have a derivation here, you have a derivation here, you have a derivation, in the nodes. Okay, so you can do by yourself. So this means that when I set, rather than, because the more elegant way is not by writing the extensive form, is to write in a compact form. Okay? So this bias condition, which reflects in one line, look at what I'm saying, one line, is the most elegant way. Okay? And this is the way you should do it. Okay? So, since you are not used to manipulate matrices and doing in a scalar form, in the extensive form, and so on, but you should get used in this way. So, I have A multiplied by X, okay? And since X is theta hat by the estimator, so I put it there, blah, blah, blah. These should be 0, and so I get the two conditions, okay? A multiplied by H is equal to identity, which is coinciding with the one that we just derived. And A mu plus B is equal to 0, which is the same here. I take this, put on the other side, and that's the second condition. So this is the most elegant. Right now, I'm using the unbiased. Okay, so I say it again, best. I make it like a joke, but it's I try to fix in mind. So best okay? The minimum mean square error, linear, that's one, okay? Unbiased. Now, when I get the unbiased, finally, I get the condition to be unbiased. So my estimator, remember, my unknown is A. My estimator should be such that multiplied by A should be identity. Now, if the matrix H is square, A is the inverse. Okay? But I don't know it. Usually H is not linear at all. So the trivial solution is not the inverse. I need to find it. Now, best linear unbiased. And now I'm estimator. Okay? Now I use the linear, fine, I use the unbiased, fine, estimator, okay. Now best. I need to use this condition. Okay? Now this condition is the second one. So I need to set the minimum of the variance for all the estimators. So if I set the minimum variance for all the estimators, that means that the variance for the estimator theta 1 should be minimum. The variance for estimator theta 2 should be minimum. So what I need to write is that I need to write the variance. So now, what is the variance? The variance for that one, can be written by this relationship. So this relationship is by just plugging in all the terms in a similar way. So when I plug in all the terms, okay, my variance on the estimated value, theta k, is A K transpose of CW, which is the covariance AK. This is a quadratic form. So this one, is a quadratic form on A. On AK technically. Okay? But then, that one is true, but it is subject to. So it's conditioned to the fact that that AK should be orthogonal to all the other H. So AK should be such that, look at here. So AK should be equal to 0 for any HI except HK. So I need to write a set of constraints. So in order to solve this one, I need to go back to the constraint optimization problem. Now, the way to solve it is by the Lagrange multiplier. So I go to the Lagrange multiplier in order to solve for that, because this is the problem that comes out. Oh, you see, Lagrange multiplier is useful for something. It's not just an aseptic and useless manipulation. It is useful to get the estimator. It's useful to get the linear estimator, which is the best. You cannot do better than this. Okay? Now, I go to the Lagrange multiplier, okay, so I go to the formula. Let me see if I have here. The formula I need to apply is those that we saw. I don't see. I think in the introduction. Here. Here. This is the optimization I'm solving. So it's a quadratic form with a set of constraints. So I take the solution, which is that one, okay? I take this solution. Of course, A has a different meaning here. A, C, blah, 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 okay? Then I plug in, and then I get the solution that is the one that, I'm discussing today. Which I lost. Yeah, okay. So this is, this is my theta hat. And that one is my estimator. So my estimator now, which is the best linear unbiased estimator, okay? So this is my estimator. It's linear, of course, I impose it. So, you know, the way to compute the estimator depends on the covariance, on the inverse of the covariance matrix of the noise. It depends on H, the linear model, and of course this is X, the data. This is the best. And then I prove you with a very stupid example that this one is the best, the real the best. Okay? So, you know, by the way, this is the matrix A. Okay? Now, if you ask me, where is B? Okay, I mean, in order to simplify the problem here, I took as mu W is equal to 0, and then for this reason, B comes to be 0. Okay? Just to simplify, you know. Now, so that's the best, you know, estimator. Now, what I can do is the following on that. Now that I have my estimator, which is in analytic form, okay? So, since I know what is X, what I can do is that I can calculate the covariance of this estimator. So, how good is this estimator? What is the covariance? Remember, in the covariance, along the diagonal, I get the variance. Okay? So anytime I have a covariance, don't make a mistake on that. Okay? So when not right now I'm computing my goal is to compute the covariance of theta hat. Okay? That is, I want to compute how good, how bad is my estimator. Okay, now that I did it. That is the estimator. Okay, that is the function. That is the linear function which is minimizing the mean square error, is linear, minimized, and is unbiased. That is the best. Best means, you know, is a best linear unbiased estimator. Now, I want to say, what is the covariance for theta hat when this theta hat is blue? Okay, which is the minimum one. So I want to see what is that one. Don't forget, the covariance, okay, contains along the diagonal the variance of theta hat 1, variance of theta hat 2, variance of theta hat b. So along the diagonal. And here there is a covariance of theta 1, theta 2, and so forth. Okay, different points. So, which means here, you know, there is the correlation among estimators. Usually, we use the variances to establish how good or bad is the estimator. Okay? So let's see, how do I get to the variances, which is, you know, these values. Okay? So these values, you know, I generally, the way I do it is by generally computing the error. Okay? So the covariance of that, what is the covariance? The covariance, you know, is computing. So this is the expectation of theta hat minus the true theta. Okay? Multiplied by theta and minus true theta Hermitian or transpose, okay, in general sense. Then I plug in into theta and I plug in that one. I develop that, blah, 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 which means what is indicated here. So what I do, you know, the error is that I plug here into here the value of the estimated value, then it is the total, you know, by the unbiased condition, it comes to be AW. So for this reason, you know, the covariance is equal to H transpose CW to the minus 1, H, everything multiplied by 2 to the minus 1. This is the closure form. Another good news, we have a closure form to the covariance. So we know exactly how the estimator behaves. Now, notice, depends on age, so it depends on the model, so it depends on the problem. And it depends on the noise. CW. Okay, so the correlation property of noise. Okay. Now let's make before computing the variance and closure form. Let's make just a digression. Let me copy and paste it this way. I just, so the covariance of theta hat is equal to H transpose CW to minus 1 H, everything to the minus 1. Okay. So now, since the covariance is a P times 1 vector, overall should be P times P. Okay. So this one is N times N, this one is N times P, and this one becomes a P times N. Just as a size, as a dimension of the problem. Now, let's make a very simple case. Let's assume, oh, by the way, let me copy that. So the estimated value, theta hat, is equal, I copy it. So it is H transpose CW minus 1 H minus 1. Then it is H transpose CW minus 1, and then it is X. Just copy. No. Let's take an example. Consider a case where CW is equal to sigma square W identity. Example. So what does it mean? It means that the noise is uncorrelated across different values. Okay. Let's see what's happening. Now, in this case, theta hat is equal to H transpose. Now, the inverse of CW, okay, this one is 1 over CW to the square multiplied by identity, because the inverse of identity is identity, times H, everything to the minus 1. Then I have H transpose. Then here I have 1 over sigma squared W, identity, times X. Okay. Now, here I have H transpose H to the minus 1, then I have a scalar. But when I have the inverse of the scalar, becomes the inverse of the scalar itself. So this one is sigma squared. So that one becomes theta hat equal to sigma squared W. Then I have H transpose H to the minus 1. Then it is H transpose. Then the identity disappears when it's multiplied by X. So it is 1 over sigma squared W multiplied by X. This and that simplify. And this one is the pseudo inverse, which is a solution of a least square. That one is the pseudo inverse, okay, which is the least square solution, which is a least square. We will see a least square estimator. So we found that the intuitive solution that we derived when we started, when dealing with Apple stocks, is optimal only when the time, the value are uncorrelated each other. Remember, the covariance should be identical. It's not statistically independent. I'm not saying that it's Gaussian. I'm not saying anything. I'm only saying that, they should have covariance equal to identity. It's proportional to the identity. Is it clear? See? And in these cases, let me continue on that, because it's more important than you can imagine this example. And in these cases, the covariance of theta hat. So I look at the formula, okay, so it is H transpose, then it is 1 over sigma square, okay, then it is H, everything to the minus 1, multiplied by sigma squared W. So the covariance is dependent on the sigma squared. So the larger is the noise, the larger is the covariance. Okay. So, and it depends on the H, the property of H. I want to make a very simple example. Sorry, I use all the, we probably take 5 minutes more than the limits, let me say, okay? Let's consider a very simple example. Let's consider that we have a set of measurements, so x1, x2, x3, x4. And each one of the measurements has a different variance. One stupid example. Assume that, I want to take the average of a set of data. I assume that, I make a measurement with the phone, okay? And when I make a measurement by the phone, and I want to take the average. But when I take the average, not every phone has the same accuracy. If I take a $1 million phone rather than a crappy phone, they don't have the same accuracy. Like MEMS, accelerometer, whatever I'm going to do. So if I take the average, that's it. Sum all the value divided by n. So if I'm averaging all the phone, so the measurement, imagine I'm making a measurement of temperature in this room, I take the mean coming from all your phone. What's happened is that if there is a crappy phone, the crappy counts as a good. See? This is the problem of Facebook, the ideals counts as a good, okay? And since the ideals talks more, so the ideals, is disseminating the idiocy, okay? So, what is the issue? The issue is that we cannot average in the simple way. We need to weight. So the good measurement has to weight more, and the crappy one has to weight less, okay? So, this is the good statistical way to do it. Are you ideal? That doesn't matter what you say. Okay? If you say something, you know what you say, okay, you count more. So now, let's see if it really happens in this way. So let's make it. So imagine now that I model the system as if x is normal with the mean that is A. So every phone has the same value A, but is affected by a covariance, so there is an error on every phone. And by the way, assume that, since the phones are in some way correlated, they are also correlated with each other. So there is a correlation matrix CX among the phone, okay? So this is the data, the input of the data. So because of that, I want to calculate the mean. Now, the way I calculate the mean is the following, I make it seriously. I don't calculate the mean as an ideal, so just, summing. I say, wait a minute, I need to be smart. So let's make it. So what I do is, the estimated mean is equal to the weighted sum of all the samples. Okay? So I'm summing all the samples. Now, how do I get weight? So alpha has to be determined. And so what are the conditions to determine? I can use blue condition. So I can use unbiased and minimum variance. So what is the unbiased? Now, the unbiased means that the bias should be 0. So let me write the condition for bias. When I write the condition for bias, means that the sum of the weight should be 1. Intuitive, right? Making the mean of numbers. So, the sum of the weight should be 1. Okay. So it's not surprising, this condition. Now let's put the variance. Now the variance is, if I write it, so it is alpha transpose covariance x, which is something I know, multiplied by alpha. So it is alpha transpose covariance x alpha. Okay? So what I should do is, I need to write then, I need to minimize alpha transpose covariance x alpha, subject to that alpha transpose multiplied by 1 should be 1. Okay? So this is exactly, you remember, we solved the problem with a quadratic form. I make it in 2D because I cannot draw more. Okay, we solved the problem with a quadratic form with a linear constraint. So what I need to do, I cut this quadratic form along this direction, and the minimum is the minimum of the cutted one, the constrained one. Now, so I go to the Lagrange multiplier, which is one page before of those that we showed before. Okay, so I go to the Lagrange multiplier, and then I get the optimal weight. So the optimal weight is this one. So I mean, might be tell you. So you might say, okay, might be right or not. No. Okay. So let me see. So these are the optimum set of weights. These are these. These are the optimal weights, where 1 transpose is a factor of 1. So when I write 1 transpose e to the minus 1, 1, there is a number. This is a number. So everything depends on the inverse of the covariance matrix of X. And the optimum variance, which is the minimum variance, is that one. Why? Let's make it simple, more simple. Let's consider the case, where now the covariance, okay, the covariance is a diagonal one. So every one of you has a phone, and every one has a specific uncertainty. Sigma 1, sigma 2, sigma 3, blah, 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 okay? So different error. You can imagine you have an accelerometer, okay? And so there is a crappy accelerometer, perfect, very good accelerometer, and so each one has some error, some uncertainty, okay? So the uncertainty goes into the sigma. Bigger sigma, bad uncertainty. Good, small sigma, very good accelerometer, okay? So remember the story, huh? So sigma k high means that the measurements are largely dispersed, okay, bad data. Sigma square k low means that they are very narrow, good data. Okay? Good. Now this is the intuition behind. Now let's put into the formula. And what comes out? It comes out that the weight that comes from blue is the sum. So it depends on the inverse of the variance for that measurement. Okay. So that means that when I have a crappy one, that measurement, sigma is big, but 1 over sigma is small. So it weighs less. If I take, a very good one, sigma is very small, 1 over sigma is very big. It's very good. And this one is just a normalization factor. Okay? And so, this is how is the blue estimator. Now, if you try, this is what is left to you. If you try to compare the variance of this estimator with the variance by computing just the mean, okay, which is just taking the mean, sum of the numbers divided by n, you will see that the variance in this case, for the estimator, the optimum estimator, is much, much lower. And this concludes the day. So, which means, if you want to put together measurement with a good uncertainty, with a bad uncertainty, you need to weight inversely with respect to the dispersion of the data. This is the conclusion about the blue estimator, which is, let me say, intuitive in some sense. But if I ask you, write it formally, you had no way to write it until today. Enjoy the weekend. and read it, check it, let me write, check